Hello everyone, welcome to topic 3.3, solids, liquids, and gases. In this you will learn how to represent the differences between solids, liquids, and gases using particulate level models. We have some essential knowledge that is tied into that, and Coulomb's law will be making a new appearance again. So in our notes, a lot of this should be review, but we're going to go back through it just so we have an even playing field for everyone. Particulate diagrams can be used, so that's when we show particles, can be used to show different properties between solids, liquids, and gases. For solids, particles do not have enough kinetic energy to move freely. They are only vibrating, so they sit and fidget in place. There is not much space between the particles because the intermolecular forces hold the particles in place. The result is a rigid, fixed volume and shape. Because of the minimal space between particles, solids cannot be compressed. The location of particles can either be crystalline or amorphous, meaning no regular structure. Crystalline solids have a repeating three-dimensional structure. For amorphous solids, the particles are disordered. However, in both cases, the molecules do not have enough kinetic energy to move freely. An example of a solid particle diagram is below. For liquids, the particles are still close together. However, the molecules have gained enough kinetic energy for them to slide and roll around. This enables the liquids to take the shape of their container. The close contact of the particles still results in the liquids being unable to be compressed. Solids and liquids of the same substance are often approximately the same size because particles are close together in both states. The temperature range where a substance is a liquid is determined by the strength of the intermolecular forces. This includes hydrogen bonding, dipole-dipole interactions, and London dispersion forces. The temperature range where a substance is a liquid can be compared by analyzing the strength of these forces. An example of a liquid particle diagram is shown on the next page for you, but right here for me. Notice that there's still some regular structure, but they are sliding and moving freely past each other. Next, in gases, the particles have gained enough kinetic energy to overcome intermolecular forces holding those particles together. This results in the particles being far apart and moving very quickly. Because the particles are far apart, gases can be easily compressed. They also take the shape of their container as the particles can move freely. There is no regular arrangement of the particles. The frequency and strength of collisions between particles is dependent upon temperature, pressure, and volume, which we will get into when we get into gas laws in another section or two. Particle diagrams can be combined to show phase changes by showing two distinct layers with properties of each desired state. So in our I do, of the following, the best explanation for the fact that most liquids cannot be easily compressed is that the molecules in a liquid, they are in constant motion, but gases can be compressed and they move more, so it's not that one. They are relatively close together. Well, that's true, and that does prevent them from being squished even more. They have varying densities. Well, nothing said anything about densities up there, so skip that one. They have a fixed volume. Well, that's true, but that might be because they are close together. And they move slower as temperature decreases. Well, that's true for everything. So the best one here is that they are relatively close together, which prevents them from becoming even closer together. Okay. And that does then lead to it having a fixed volume, but that the fact that they are closer together is the primary reason. So now in the particle diagram, I want you to pause the video and draw a puddle of water as it starts to evaporate. So consider the two phases if it's evaporating, it's two phases, phase change, that are going to be present, and how you would represent them differently. So please pause the video and attempt that now. Okay, so it should look a little like this, where we have a gas phase and a liquid phase, where in the liquid they are closer together, but they are randomly ordered, and the gas phase they are further apart and also randomly ordered. To improve on this, we can draw movement arrows to show that gases are moving randomly and very fast, but that liquids, though they still move at a lower temperature, randomly sliding past each other. So they still move, but they're stuck within themselves. Okay, so using this information, go ahead and work on the you-dos. You might want to reference to 3.2 notes to help you with the first you-do especially. Thank you, everyone.